All right, welcome. If you're getting ready for your AQA GCSE Physics exam, you are in exactly the right place. We're about to break down section 4.3.2, which is all about internal energy, heating, and changes of state. So let's just dive right in. So, to get our heads in the game, let's start with something you've probably noticed 1,000 times in the kitchen. You've got a big pan of water, and it just takes forever to boil, right? Much longer than a small one, even on the same stove. But why? Well, the answer is all about the physics of internal energy. And by the end of this, you're going to get it completely.
So here's our roadmap. First, we'll nail down what internal energy actually is. Then we'll look at how heating changes temperature, what's going on with energy during state changes, and the big one, the difference between regular heat and latent heat. And finally, we'll wrap it all up with your exam essentials. Okay, let's do this. Right, section 1. What on earth is internal energy? To get this, you have to imagine zooming way in. I'm talking down to the particle level. Everything, absolutely everything, is made of billions and billions of tiny particles, and they are never, ever still. Okay, this right here is the official AQA definition you need to know. Write it down, memorize it. Internal energy is the total, and that word is so important, it's the total kinetic energy and potential energy of all the particles in a system. It's not one or the other, it's both added together. So let's pull that apart. First, you've got kinetic energy. The easiest way to think about this is movement energy. It's the energy particles have because they're vibrating, jiggling, and zipping around. Then you've got potential energy. This is a bit different. It's the energy that's stored in the bonds between the particles, the stuff holding the whole structure together. So if internal energy is made up of these two parts, how do we change it? Well, the most obvious way, right? We add heat. Let's take a look at how that actually works. Now, this is the part we all experience every single day. When you heat something up, you're basically just giving its particles a big energy boost. They start moving faster and faster, their kinetic energy shoots up, and what we see and measure on a thermometer is the temperature rising. Simple as that. But here's the catch. Not everything heats up at the same rate. Some substances are just, well, they're more stubborn about changing temperature, and that property is called specific heat capacity. Water, for example, has a crazy high specific heat capacity. That's why it takes so much energy and so much time to boil that big pan of water we talked about. And of course, in physics, we have an equation for this. This one will be on your formula sheet, so you don't need to memorize it, but you do need to know how to use it. It tells us that the change in energy is just the mass of the stuff times its specific heat capacity times how much the temperature changed. Oh, and here's a massive exam tip. Your mass has got to be in kilograms. They love to trip people up with that one. Okay, so heating makes things hotter. Got it. But what happens if you keep pouring energy in and the temperature just stops going up? This is where things get really, really interesting. Seriously, picture it. You've got that pan of water boiling away. The thermometer says 100 degrees Celsius. You keep the heat on full blast, pouring energy in, but that thermometer just stubbornly stays at 100. It doesn't budge. So where is all that energy going? It's going into changing the water from a liquid into a gas, into steam. The energy is being used to literally break the bonds holding the water molecules together. So you're not increasing their kinetic energy anymore, which is why the temperature doesn't rise. Instead, you're pumping up their potential energy. The particles aren't moving faster, they're getting further apart. And the energy needed for this special job has its own name. Specific latent heat. The word latent literally means hidden. And that's perfect, right? Because it's the hidden energy that's doing all this work in the background without any obvious change in temperature. And yep, you guessed it, there's an equation for this too, also on your formula sheet. The energy needed is just the mass times the specific latent heat, or L. And notice what's missing here? There's no temperature change. Of course there isn't, because during a change of state, the temperature stays constant. Now, there are two types you need to know. Fusion is just the fancy physics word for melting, so that's for going from solid to liquid, and vaporization is for boiling, when you go from a liquid to a gas. And just so you know, the amount of energy it takes to melt a kilo of ice is very different from the energy it takes to boil a kilo of water. Okay, this is probably the biggest point of confusion for so many students, so let's put these two ideas head to head. When do you use which equation? Let's make it super clear. This table is your absolute best friend. It boils everything down.
If a question says the temperature is changing, you know you're dealing with specific heat capacity and the first equation. If it says the state is changing, like ice melting or water boiling, you know it's specific latent heat, and you use the second, simpler equation. It really is that straightforward.
Phew, okay, we've covered a lot of ground. So let's filter all that down to the absolute must-know, can't-forget facts for your exam. This is the stuff you really need to lock in. Let's run through the checklist one last time. Internal energy, that's kinetic plus potential. Temperature changing, you're using delta E equals mc delta theta. State changing, that's E equals ml. Specific heat capacity is for temperature change. Specific latent heat is for state change. And the golden rule for both, your mass must be in kilograms. Don't throw away easy marks on that. Okay, to finish off, here's a little puzzle to really test your understanding. Imagine you have an ice cube and a glass of water, and they are both at exactly 0 degrees Celsius. Their particles have the same average kinetic energy, right? But which one has more total internal energy? Think about the bonds. Think about the potential energy. Which one had to absorb all that hidden latent heat just to get to where it is? That's your clue. Good luck with all your revision.